In the study of data structures, it is natural to begin with one of the simplest data structures, which is a stack. So in this presentation, we will examine stacks from an abstract perspective and also consider a variety of possible concrete implementations. Let's begin with how we might describe the stack data structure abstractly as an abstract data type. Every data structure can be described in this way, using the language of mathematics. Although we won't use this formal approach with every data structure, doing so with the simplest one will help clarify how a data structure can be described apart from any details of how it is actually implemented. Recall that the abstract components of a data structure include the interface and the behavior. So let's start with the interface. It requires defining the operations, but before we can describe them, we must begin with the associated data types, or viewing them mathematically, the sets that are involved. All data structures are containers, so we will always have at least two kinds of sets. The first set is the set of components. In terms of Java generic classes, these components are defined by the generic formal parameter of the class definition. The other is the set that defines the data structure, which in this case is the set of stacks. Now we can define the interface, which consists of the specifications for each operation. Mathematically, we view these as functions. The first operation is push, which we have designated as theta. It takes a stack and a component and returns a modified stack, one which has the element added to its top. The other fundamental operation is pop, which we designate as row. Given a stack, it returns a component and a new stack with the component popped off. Finally, we need a designation for an empty stack, which we symbolize with a 0. This is what is referred to as a zero-order function, meaning we don't supply it anything, it just gives back an empty stack. This is not to be confused with a function that tests whether a stack is empty, which in an actual implementation is more useful. Next, we need a formal way to describe the behavior of these operations. Although in most documentation we would provide an English description, a mathematical description is more precise. We refer to these as the axioms, meaning what we expect to be true for this data structure. The first one says, for all stacks and all components, if we push a component onto a stack and then immediately pop it off, we get back the original stack and the component we just pushed on. This is a formal way of saying that a stack is a last in, first out data structure. The next one is a description of what happens if we try to pop an empty stack. We get nothing back and the stack is still empty. Now in our implementation, what will likely happen in this case is that an exception will be thrown. But that is really an implementation detail. Next, we define the stack abstract data type using a Java interface rather than mathematics. The advantage of first defining an interface is to ensure that various representations are interchangeable. By ensuring that all our stack representations adhere to an interface, we achieve loose coupling. In any program that uses a stack, it will be possible to replace one implementation with another without changing the behavior of the program. This interface, together with its implementation and associated exceptions, will be in the same package, stack. Because all data structures are container classes, the interface that defines them will be generic interfaces. The type of the components is specified by the generic type parameter T. First, the push. Because these are methods of a class, the stack itself is not an explicit parameter, but when we invoke the method, we will of course specify onto which stack we are performing the push. What is supplied as a parameter is the item we are pushing on. Its type is the type of the components, which is defined by our generic formal parameter t. Because one of our implementations will use an array, it will be necessary to fix the size of the array when the stack is instantiated. So it will be possible that the stack can become full, which is why we include the possibility of throwing the stack full exception. A similar implementation that used an array list or vector, as the Java stack class does, alleviates this problem, because with those classes the underlying array can be expanded by allocating a larger one and performing a copy. Of course, all computers have finite memory, so it is still always possible to run out of memory. The other fundamental operation is the pop. It will return the item popped off, which is why the return type of this method is our generic formal type t. Regardless of whether we implement a stack with an array list, or a linked list, the possibility that the stack will be empty must always be considered, which is why this method is designated as potentially throwing the stack empty exception. The final method is the isEmpty method that checks whether the stack is empty and returns a Boolean indicating whether or not it is empty. Providing this method helps the user ensure that the stack empty exception is never thrown. What we haven't included is the part of the abstract view that is the English description of the behavior. In comments, we would need to describe its last in, first out behavior, which is typically what one sees in Java docs documentation. Now that we have described the behavior of a stack abstractly, both mathematically and with a Java interface, let's consider the various ways we might implement it. We begin always with an array-based representation, which is the simplest. We will examine the code for the two fundamental operations. This representation will require two instance variables, an array and a subscript that points to the top of the stack. We name this class ArrayStack. It is a generic class that implements the stack interface that we just discussed. Because it is always a good practice to ensure that the representation is hidden, both variables are declared private. We named the array stack. Note its type is an array of the generic type t. Because we cannot instantiate an array whose type is a generic type, we must instantiate an array of type object and then perform a typecast. We chose an arbitrary size of 200. One way to make it a bit more general would have been to provide a constructor that supplied the size and instantiate the array in the constructor. Fixing the size avoids the need for an explicit constructor. We rely on the default constructor that Java supplies. Top is the other instance variable of the class. Notice that it is initially set to 0 to designate an empty stack. So in this implementation, it refers to the next available slot, not the one last used. Recall that the concrete components of any data type include the representation and the implementation. The remainder of the class consists of the implementation. The implementation of any data type is contained in its method bodies. So let's examine them. The signature of the push method is identical to how it was written in the stack interface, as it must be. Although we have omitted it here, adding the override annotation is a recommended practice to ensure that it does indeed match exactly. Inside the push method, the first check is to see whether the stack is full. When top is equal to the length of the allocated array, the stack is full and the exception will be thrown. If space is available, the push will succeed, and the item supplied will be placed at the location that top is currently pointing to. We must increment top to now indicate that the stack now has one more element and its top index is one greater than before. In this case, it is important that the incrementation of top be a postfix increment. It must be done after the assignment is performed. The signature of pop, again, must match how it is defined in the stack interface. Like what was done in push, checking the possibility of an empty stack is the first step here. As we noted previously, the instance variable top will be 0 when the stack is empty. So that is the check we are making in the if statement. If it is not empty, the element at position top -1 is returned. Using a prefix decrement is essential, just like the postfix increment was before. It ensures the top is decremented before it accesses the element to be returned, and then decreases top by 1, to reflect that the stack now contains one less element. Finally, because the stack is empty when top is 0, isEmpty simply returns the result of that comparison. As we have repeatedly mentioned, every data structure has both an array-based and linked representation. Now we will consider how we would implement a stack using a linked list. Because this is our first look at linked lists, let's begin with how they differ from arrays. Linked lists contain one node for each data element. These nodes do not need to be in adjacent memory locations. Unlike arrays, linked lists only use as much memory as needed. Every time a new element is added to the linked list, an additional node will be dynamically allocated. There is a trade-off, however. Unlike arrays, linked lists require links for each node, which adds to the memory usage. Singly linked lists require a forward link, and doubly linked lists require both a forward and backward link. There are some compression techniques that can reduce the memory needed for doubly linked lists, but those details are beyond our current discussion. A linked stack is the simplest implementation of a linked list because the push and pop operations are both done at the head of the list, which is another reason the stack data structure is a good one to begin with. Next, let's consider the Java code needed for the linked stack, beginning with its representation. The representation requires the definition of a linked list node and an instance variable that points to the top of the stack. We name this class linked stack. Like the array stack, it is a generic class that implements the generic stack interface. Every linked list requires a class that defines a node of the list. We have elected to define it as a private nested class. There are trade-offs to this design. This approach has the advantage that it hides the representation. On the other hand, using a public class that is not nested would allow multiple data structures to share it. Note that it is declared static because it is not an inner class. When there is no need to access the instance variables of the outer class, this designation is preferable. Notice also that it is a generic class with a type parameter t of the outer class. There are two components to this class. The first is the data element of type t. It represents the left half of the node in the diagram to the right. Because this is a singly linked list, there is only one link. Because the data structure we are building is a stack, this link points to the previous node, hence our choice of its name. Often the name next is used when we are creating a general purpose singly linked list. Notice the type of this variable is the same as the class itself, which is why this is a recursive, that is, self-referential data structure. The instance variable top is a reference that points to the top node. Because it is just a node reference, not a node, it is depicted as a single box in the diagram on the right. Finally, the remainder of the class consists of its implementation. The first fundamental operation is push. As with the array implementation, the signature for push matches the one in the stack interface. The first step involves dynamically allocating a new node and saving a reference to that node in the local variable newTop. The item passed in as a parameter is placed in the data half of the object. For simplicity, we have illustrated this action as though the value is placed there. Keep in mind what is actually copied is a reference to the object. If this class is instantiated with an integer, for example, the reference to an integer object is copied. Next, the reference contained in top is copied to the previous half of the new node named previous, because the new node now needs to point to the node that was previously the top. Finally, top now needs to be changed to point to the new node. The variable newTop is a local variable and will no longer exist once this method completes. The other fundamental operation is pop. Again, the signature for pop matches the one in the stack interface. No matter how a stack is implemented, we need to check whether it is empty. When a linked stack is empty, top will be null. That is because when the stack is instantiated, top is not explicitly initialized, so it is null by default. Symbolically, the diagonal line in the bottom node represents a null, which is why when the last item is popped off, the stack will become empty again. Because pop needs to return the value at the top of the stack, it must be saved before the top node becomes inaccessible. So at this step, it is copied to the local variable item. The assignment of top to top previous copies a reference to the second node in the list to top, which has the effect of removing the top node. Finally, the data that was saved in the local variable item is returned. Because Java has automatic garbage collection, there is no need to explicitly deallocate the memory that this node uses. Once top was reassigned, there are no longer any references to it, so the deallocation is automatic.